Good morning.
Good morning, Kaida. Can you let me know what do you see right now? Do you see the note?
Yeah, I see Newman number 5.
Okay, cool. Very good. Just want to make sure. Nine 30. I see Kaida, Bailey, Max, Ether, Eliza. So 1, 2, 3, 4, 5. Do we only have 5 participants? Okay, we have Jose here. So 1, 2, 3, 4, 5, 6. And that's all. Let me mark attendance. Kaida is here. Michael, is Michael here?
Here.
Max is here. Okay, Michael is here. Okay, awesome. The other section. Jose is here. Is
Here.
Elisa here? Elisa Haley. Absent. Eliza is here. Bailey's here. Ether's here. All right, very good. I just want to double check you guys are able to see my note, right? This is the unit 2 note. Okay, so we're gonna start unit 2 today. And we talk about complex numbers today. And what is a complex number? We're gonna start from understanding what is the imaginary unit. Anybody can help me to solve this equation? Anyone can help me to solve this equation? Find the solution or solutions for this equation. What value of x would satisfy this equation? Which value whose square gives -1? And let me know your answer. You can unmute yourself or you can type your answer in the chat.
X equals the square root of -1.
X equals square root of -1. Okay. Now what is square root of -1? And by the way, plus minus. Okay, this equation has two solutions. And what is square root of -1?
Isn't
It
it
is
just I?
Okay, so you are ahead. Unless you have learned complex number in foundation 2, in real number set, square root of 91 does not exist, right? In other words, square root of 91 is not a real number. Square root of 91 is not a real number because in real number set, the radicand under a square root has to be non-negative. Okay, if the radicand of a square root is negative, the radical is undefined. Well, in real number set, this equation has no solution. Let me write it down. In R, this fancy capital R represents the real number set. In real number set, this equation has no solution because there's no such a real number. Multiplied by itself will give a negative number. We know any number, any real number, whose square is going to be a non-negative number, right? So for that reason, mathematicians bring in or expand the real number set. They expand the number system. They really want to solve this equation. They have to expand the number system. And they define square root of 91 as I. And I is the imaginary unit. I is the imaginary unit. And I is not a real number. It is not a real number. And this equation x squared equals 91 has two solutions. X squared equals 91 has two solutions. The two solutions are I and -I in complex number set. In real number set, this equation has no solution. If we really want to solve the equation or find the solution or solutions for the equation, we have to expand the number system and consider the number system as a complex number set. Real number set is the subset of complex number set. In a complex number set, this equation has two solutions. The two solutions are I and -I. I here is defined as square root of 91. Let me highlight the formula that you need to know. I is defined as square root of 91. Again, it is not a real number. It is called the imaginary unit. It's not real, it's imaginary. It's not real, it's imaginary. It's interesting, the name, right? Okay, with the imaginary number, we can give the definition for a complex number. How the mathematicians expand this number system from real number set to complex number set. What does a complex number look like? The standard form of a complex number look like this. A plus bi. There are three components in this form, in the standard form of a complex number. The three components are A here is the real part. It is a real number, okay? A is a real number. I can just write A is a real number. Is called the real part of the complex number. B here is called the imaginary part. Imaginary part. B here is the imaginary part of the complex number. It is also a real number. I here we have just covered. I is the imaginary unit. When you learn a language, you do need to recite the vocabulary and the grammar. This is mathematics in language. It is necessary to know those terminologies. And the imaginary part and the imaginary unit is often being confused with one with the other. So we must know A here is a real number. It could be any real number. It could be positive, it could be negative, it could be zero. B is the same thing. A, B here are real numbers. They could be any real numbers, positive or zero or negative, rational or irrational, fraction or decimals. A, B here are real numbers. A is called the real part of the complex number. B is called the imaginary part of the complex number. I is not real number. Remember, what's I? I is square root of 91. It is not real. It is the imaginary unit mathematician define. So that's the standard form of a complex number. Any number that can be written in this form is a complex number. Any number that can be written in this form is a complex number. Let me give you some examples you determine. You tell me, are they complex numbers or not, okay? I give you 4 examples. Just put it here, later I have to erase. The first one, 2 plus 5i. Is 2 plus 5i a complex number?
Yeah.
Yes. If it is, can you tell me what's the real part?
2.
Correct. What's the imaginary part?
5.
Awesome, very good. Knowing imaginary part is the coefficient, you can see 5 here, the imaginary part, as the coefficient of the imaginary unit. We know what is coefficient, right? The number in front of a variable or, something else that they multiply together. Number 2, negative 3i. Is this a complex number? Negative 3i.
Yes.
Yes, but it doesn't look like that, right? It doesn't look like that is because the real part of this complex number is 0. We can write negative 3i as 0 plus negative 3i, right? Then this number is in the standard form. It is a complex number. Negative 3i is a complex number. Real part is 0. 0 part is 0. Imaginary part is negative 3. Be careful with the sign. I is the imaginary number. Unit, I'm sorry. I is the imaginary unit. Number 3, 2. We all know 2 is a whole number, is a natural number, is a rational, is a real number. We are very familiar with this number, right? Is this number a complex number? We just learned what is a complex number. Is 2 a complex number? Again, any number that can be written in this form is a complex number. Are we able to write 2 in that form? Give it a try. Can we write 2 as 2 plus 0 times I? Sure, right? Yes, 2 is also a complex number. 2 is a complex number because we can write 2 as 2 plus 0 times I. It is in that form. 2 here is the real part. 0 here is the imaginary part. I is the imaginary unit. And number 4, 0. I'm gonna tell you any number, okay? Any number is gonna be complex number. Any number are gonna be complex number because they all can be written in that form. Even zero. Zero can be written as 0 plus 0i, with both the real part and the imaginary part as zeros. And I here is the imaginary unit. Okay. Number 3 here, complex number set and the relationship between C and R. C here is supposed to be a fancy C. R here is supposed to be a fancy R. C here represents the complex number set. R here represents the real number set. And complex number set is just defined as the set of all complex number, right? Oh, sorry, I wrote the wrong place. Complex number set C is the set of all the complex number. A, B are real numbers. I want you to see that. Look at the definition of the complex number set. I want you to see that real number set is a subset of the complex number set. In other words, I want you to see all real numbers are complex numbers. Real numbers are part of complex numbers. Real numbers are complex numbers when the imaginary part B is 0. B here could be 0, right? When B assumes that value 0, then the complex number actually is a real number. Do you see it? Real numbers are part of the complex number set. When the imaginary part of the complex number is 0, the complex number actually is a real number. All right? Next, geometric significance of complex numbers. Okay, so I want to start with the geometric significance of real number set. I don't know if you remember this. There is a one-to-one correspondence relationship between any number in the real number set. Real number in the real number set, and any points on the real number line. Okay, we should know what's a real number line, right? Real number line is a straight line with 3 components. Direction, we can define this is positive, this is negative, and origin, we can put pick any point as the origin. We can maybe choose the point in the middle as the origin, right? And then define the length of the unit. I can say this is 1 unit, this is a 1. Then this is 2, 3, 4, 5, and so on. This is 91, 92, 93, 94, 95, and so on. How many points on this real number line? Do not tell me 10. I just label 11 of them, right? Include 0. In fact, there are infinitely many, uncountably many points on this real number line. Both directions go to infinity. So there are many points. I hope you see that. Many points, right? So there are infinitely many, uncountably many points on the real number line. And that's how many real number set. That's how many real numbers in a real number set. That's how many real numbers in a real number set. In fact, there is a one-to-one correspondence relationship between the real number in a real number set and the points on the real number line. That means for any real number, there is a unique point on the real number line representing it. Vice versa, for any point on the line, there is exactly 1 real number correspond to the point. And so sometimes we don't really differentiate one from the other. They are actually the same thing in different form. A real number, for example, 5, is the algebraic expression of this point. And that point is the graph or geometric significance of the real number. So they are the same thing in different form. The real number is the form in algebra. The point is a concept in graph. So understand this would help us understand how do we understand the graphical significance of complex number. Complex number look like this, right? A plus B, A plus BI. In complex number set. You know what there is? This means a correspondence. Okay, this is not a real number line. It's very short. There is a one-to-one correspondence between the complex numbers in the complex number set and points in the rectangular coordinate system. This is a rectangular coordinate system, all right? When we talk about graph on a plane, two-dimensional space, and that space is a rectangular coordinate system. Also, it's called a Cartesian plane. You might have already seen that name. How many points on this plane? How many points on this plane? And knowing this is forever, continue. So there's no bound, all right? There's no boundary. How many points there?
Infinite.
Yeah, everywhere, right? Infinitely many, uncountably many. If you want to know what is uncountably, I'll find another chance to explain. Many, all over the places, right? Basically, the system is made of those points. Because of those points, the system exists. And that's how many complex numbers we have. That's how many complex numbers we have. There is a one-to-one correspondence relationship between the two. Yeah, also this is the algebraic expression. This is the graphical expression. They, in fact, is the same thing in two different forms. Very similar with earlier when we talk about the real number and the point on the real number line. That's one dimension. Here is the two dimensions. Just one more dimension. One more dimension. From a line, now we have a space. We have a plane, two-dimensional space. And for example, the complex number 1 plus 3i. How do we find the point in the rectangular coordinate system that representing the complex number? So firstly, we need to identify the real part and the imaginary part. 1 plus 3i has a real part 1, imaginary part 3. And you put them together, use a comma to separate the two parts, and use a parenthesis to frame, and we get a point in a rectangular coordinate system, right? It is in quadrant 1, 2, 3, 4. So since both the two components of the point are positive, is in quadrant 1. This is the origin. So first component is 1, so we go to the right 1 time. Second component is 3, so go up 3 units. So this is 1 plus 3i. Okay? That black point is 1 plus 3i. So far, so good? Can I give you one more? Can you help me to find the negative 4i? Can you help me to plot negative 4i?
It's going to be at -4 on the x-axis.
On the y-axis, right? Here is negative 4i. Very good. Negative 4i is 0 minus 4i. with the real part 0, imaginary part 94. 0, 94. That point is on the vertical scale. When we have a complex number whose real part is 0, then that complex number is called non-real imaginary number. It's called a non-real imaginary number. It's called imaginary number. And the points are on the y scale, y-axis. And how do we plot 3? How do we plot 3? 3 is a complex number. It is a real number with, but we can write the number as 3 plus 0i. So it is also a complex number. Real part is 3, real part is 3, imaginary part is 0. So the point that represent this complex number is 3, 0 right here. All right. So I want to be able to see all the points in the system, rectangular coordinate system. They make the complex number. They make the complex number set. But points on this line, on the horizontal scale, that's the real number set. Do you see what I'm trying to say? The whole two-dimensional space, this rectangular coordinate system, the tens of infinitely many, uncountably many points, right? That gives the complex number set. All right. But that red one, the horizontal scale, x-axis, the points on the x-axis, they represent real number set. Points on that scale, horizontal scale, they are real numbers. They are real numbers, but not they are not. They don't have an I in it. They are, of course, complex number, but they are real numbers. How about I can say this other point? The points that are not on the red straight line, the red scale, they are not real numbers. Do you see what I'm trying to say? Another way to see why the real number set is a subset of the complex number set. The real number set is this real number line, the horizontal one, not the vertical one, okay? Only the horizontal one. And the complex number set is the whole plane. So obviously, real number set is a subset of the complex number set. Those concepts would help us to understand complex number better. Next. And let me know if you have questions, all right? How come I don't have... Okay. Next topic. Formula to compute the value of the square root of a positive number. Formula to compute the value of the square root of a, negative number. In real number set, square root of -10 is undefined, but in complex number set, it is well-defined. Square root of -10 is a complex number. Then how do we write the complex number in the standard form? The formula is this one, is this formula, okay? Is this formula. So I'll write you some examples, and then you will understand how to apply that formula. Very simple. For example, square of -10, you just need to write it as square of 10 times I. If you really need to write a standard form, then you have 0 plus root 10 I, and that's it. But normally, we don't really write a 0 out. It's a root 10 I, okay? And another example, square of -5, square root of a negative number. Get rid of the negative sign, square of 5, but multiply I. square root of negative half, it is square root of half times I. Square root of negative 100, root 100 I, root 100 is 10, so 10I. So do you see how should you apply the formula? You do not have to struggle with the formula. I notice students have trouble to memorize or use a formula because it looks very abstract. But I just show you how to use that formula. That formula is to rewrite square root of a negative number as a complex number with I in it, with something in I. How about that? We use that formula to rewrite a square root of negative number as something in I. And that's how you do it. Any questions? Any questions?
No questions.
Okay, and I need to write down a sentence. And I hope you can include that in your note. Note, whenever you see a square root of a negative number, the first thing to do is apply the formula. Okay, whenever you see a square of a negative number, apply the formula right away. I have a reason. We can revisit this note later. I include a table. This table gives the perfect squares of the first 20 natural numbers. And I want you to spend a little bit of time to get familiar with those perfect squares. Those numbers are special. They are special, so when you see them, you should be able to identify them. You should know why they are special. Okay, when you see 1, you should know 1 is the square of 1. When you see 4, you need to know 4 is 2 squared. 9 is 3 squared, 16 is 4 squared, 25 is 5 squared, 36 is 6 squared, 49 is 7 squared, 64 is 8 squared, 9 squared is 81, 10 squared is 100. I believe that you know those. And when we have 11, those might be a little bit not very familiar. Yeah, 121 is 11 squared, 144, 169, 196. Okay, I'll give you a little time to look at them. When you see them later, I hope you can identify they are special because they are perfect squares. 225 is 15 square, 256, 16 square, 289, 17 square, 324, 18 square, 361, 19 square. Okay. Some of the questions in Lumen requires you to simplify a square root. Okay, for example, earlier, I give you a formula that you can use the formula to rewrite a square root of a negative number, right? Let's say it's negative 20. And the first thing, when you see square root of negative number, use the formula right away. Rewrite this expression as root 20i. But this, it is correct. But if you enter that result in the system, it will be marked as wrong because it's not simplified. Because it's not simplified. When you have a square in the expression or your result in an expression, you need to simplify the expression. Okay, square of 20 is not simplified. Now I'm going to show you 2 different methods to simplify a square root. To simplify a square root. The first method is use the big L technique. I have that technique in my video of my Foundation 2 video. Not this course, is the prerequisite course, the beginning of the class. This technique is actually very important. And 2, 5, So we can write square root of 20 as square root of 2 times 2 times 5. I can use dot instead of use that symbol. 2 times 2 times 5, right? And then 2 times 2 is 2 to the power second, and then times 5. If you have a square root in the radicand, and I also want you to know the name of the radicand. It's called a radicand. In the radicand, we have a perfect square. You know, this square will cancel the square root above the base 2. So the square cancels square root because squaring and the square root, they are reverse of each other. We have learned an inverse function, right? So you should know what does that mean. It's like you standing here, you walk to the right 3 steps, and you walk to the left 3 steps. Those two processes cancel each other. Here, you square a quantity, and then you take a square root, and you go back to the original number. So that's why when the base has a square on the shoulder, then the square can cancel the square root, and then we can release the 2 outside. But the 5 has to stay under the square root because 5 does not have the square to cancel the square root. If you do not like this method, I can give you another method. You can do this, okay? Some people think this method has better visual benefit. They do a tree. Whatever you can think. Square root of 20, maybe you think square root of 2 times square root of 10. Whatever you can think to write 20 as the multiplication of 2 numbers. For example, you think 20, you can think maybe 20, okay, I know 20 is 4 times 5. Okay, write it down. Square root of 4 times square root of 5, right? And don't forget, there's a square root symbol. You have to carry down all the time. And the square root of 4 is 2, right? And you have 2 and the square root of 5, and done. Or you can do this, square root of 2, and square root of 2 is already simplified. And square root of 10, you can continue. 10 is 2 times 5, so root 2, root 5. And then you multiply, you bring this down, square root of 2. So you have square root of 2 times square root of 12 times square root of 5. And those two multiplied together is 2, so root 2 root 5. How do we know if a square root is simplified? When a radicand, in this case here, square root of 5 is simplified because 5 does not have any perfect square factor. A square root is simplified if the radicand has no perfect square factor. The only way to factor 5 is 1 times 5. And there's 1, we don't really count 1. Am I clear? Since this is not the focus of this section, but it's actually pretty important. I want to make sure that you understand one of the 2 methods. Which method do you like? I think the second method probably is easier to handle. But if you took my foundation, you might like the first method a lot. With the skill grasped, you can very easily to simplify a square root. But without taking my class, if you didn't learn this technique, try the second method. Okay, anything that you can think. 20 is 4 times 5, right? And square root of 4 is 2. And square root of 5 is already simplified. There's nothing we can do to square root of 5. So the simplified form is 2 root 5. And if the beginning, you don't do 4 times 5, you do 2 times 10, that's okay. And root 2 is already simplified. And root 10 can keep going, right? Root 10 can be written as root 2 times root 5. And now we have 2 root 2's. And they multiply to 2. And we have 2 root 5. Response, please. Do you like the second method?
I like the second method better.
Okay, that's what I thought. Awesome, very good. Then let's practice something, all right? We're gonna practice 6 problems. I'm gonna bear with me, take a little time to get the problems in Lumen. Number 1 to number 4. Number 1. This is number 1. Simplify rule -9. When you see square of a negative number, remember right away, use the formula rule 9i. Well, you have to simplify. What is rule 9? That's easy, right? Rule 9 is 3. 3i, done. Is that easy? Is that doable? Is that doable, guys?
Yes.
Okay, awesome. So that's the first question. And number 2. Rule -18. And how do we do that? Rule -18 right away. Rule 18i, right? Well, you have to simplify rule 18. Try the technique. Maybe you know 18 is an even number, so rule 2, rule 9, right? And rule 9, you know, is 3. So this is 3. So 3, rule 2 times 3 was 3, rule 2. Normally we write the rule 2, the radical after a rational number. We write the rational number in front of the radical. So we have 3 rule 2i, okay? Oh, my bad. That one is 3i. This is 3 rule 2i. Number 3. How about you try number 3? Number 3 is square root of -25. Yeah, give it a try. Square root of -25. Share your answer.
Four plus 0 plus 5i.
Oh, actually, you're right. I didn't see the 4 there. It's more complicated. Yeah, 4 plus rule -25. Can you say that again? I'm sorry,
Yeah.
Michael. Yeah,
4 plus 0 plus 5i.
4 plus 0 plus 5i.
5i.
We don't really have to write a 0, but thank you for the consideration. Yeah, it's a 4 plus 5i. Okay, it's a 4 plus 5i. Very good. Perfect. Yeah, we don't need that 0, but you did a great. Next one, express this as a complex number in standard form. Okay, let's see, how do we do that? Rule 99 minus rule -175. The first part of the expression is a square root, but it's a square root of positive number. Well, you still have to simplify it, okay? Even if it's a positive, you still have to simplify it. Let's use the technique. In the space, rule 99 can be as, you know, 99 is 9 times 11, right? So rule 9 is rule 11. And we know rule 9 is 3. So this part is 3. 3 rule 11. So we simplify that. And minus square of negative is square root 175i. And now we need to simplify square of 175. Square of 175. If the last digit of number is 5, the number is definitely divisible by 5. Let's see what is 175 divided by 5. 3. 35, right? Is 35. So we can write this as root 5 times root 35. Root 5 is already simplified, but root 35 can keep going. Root 35 can be written as root 5 times root 7, right? 35 is 5 times 7. And now we are done. Yeah, bring this one down. So root 175 is root 5 times root 5 times root 7. And root 5 times root 5 is 5. So square root of 175 is 5 root 7. And then bring down I. So the correct answer here is 3 root 11 minus 5 root 7 I. Do you see it? To be honest, the formula to rewrite a square of negative number in something in I is just very easy. The challenging part is the simplifying the square root part. You have to simplify. So far, so good, everybody?
Yes.
Okay. So now we have 1 to 4. Now we go to 18 and 19. Lumen 18 and 19. 18 and 19. 18. 18 actually is the same with what we have done earlier. Try this one. And 19. Feel free to share your answer.
Zero plus two square root of 5i.
Perfect. Exactly. 0 plus 2 root 5i, right? I think without a 0, I think you really don't have to have 0 here. Okay. The reason because it doesn't really say write the radical in the standard form of a complex number. It just says simplify. So when we say simplify, you don't really want to have any redundancy here. Okay, next one. Simplify square root of negative 180. Try that. Don't forget there's a negative sign outside. Yeah, this is important detail. There's a negative sign in front of the square root. Feel free to share once you're ready. You want me to do it? So this expression is a negative of the yellow, right? Or you can understand the green negative sign as opposite, or just negative sign. We want to handle the yellow part first. Let's do the yellow part. The yellow part is square root of 180i. Sorry, my bad. Square root of negative 180. And we can rewrite that as square root of 180i, right? And then let's simplify square root of 180. We can do root 10 because 180 is 10 times 18, right? And 10 is 2 times 5. 18 can do 2 times 9, right? And we can bring this down root 2, bring this down root 5, bring this down root 2. And root 9 is root 3 times root 3. Or just the 3, right? So root 2 times root 2 is 2. Root 3 times root 3 is 3. And then we have 1 factor root 5. So we have 6 root 5. Square root of 180 is 6 root 5 I. So in other words, the yellow part after simplify is 6 root 5I. Don't forget, we have the green negative sign. So the correct answer is negative 6 root 5I. And done. Hope I have the same answer with you.
No.
One thing, yes or no?
Yeah, I didn't get the answer. Can we say for the 180 we can get
41.
9 times 30, like
9 times 20.
30. I know it's 3 times. No, 9 times 20, yeah. And square root of 9 will give us 3. Can it be easier that way?
Yeah, actually, you are very smart. So what happened is, because we just had a negative root 20, root 20, and
Yeah.
root 180 is just the root 20 times root 9, right? We just
Yes.
had a root 20, which is 2 root 5, and the root 9 is 3. So 2 times 3 is 6 root 5. The way that you simplify using this technique is not unique. It's not unique. It's pretty flexible. The important thing, the result is the same. Do you have the same result? How come? So 180 is 20 times 9, right? So root 180 is root 20 times root 9. Agree? So far, so good?
Yeah.
Okay. And you said root 9 is 3. That's
Yeah.
perfect. So we have 3 here. And what is root 20? Just now, didn't you guys practice? Root 20 is 2 root 5.
Okay, so I can't just leave my answer as 3 root 20. I have to break it down again.
Break what down again? You have to
break it down. Yeah, that's what I'm saying. I was thinking my answer was 3 root 20. So the root 20, I can't just leave it that way. I have to
no.
simplify it again.
Yeah, you have to simplify again.
Okay.
Yeah, that's the thing what I said earlier. How about let's write it down. This actually is important. How do we know a square root is simplified? So when we simplify something, you must be clear about the criteria. How simple is simple?
Yeah.
Yeah, that's a very important thing. So I mentioned this sentence, but I'm gonna write it down, okay? A square root is simplified if the radicand. Do you guys know what is radicand? Sometimes my coworkers say you should not use those fancy terminology in mathematics. Why not? We are learning mathematics. Why don't we learn the fancy terminology? They're important terminology. So radicand is whatever the whole thing under the square root, under the radical. Okay, a square root is simplified if the radicand has no perfect square factor. That's the standard to determine if a square root simplified or not. And you are right, to simplify something, you must know how simple is simple. When you have 3 root 20, that's not done yet, because 20 has a perfect square factor. Well, maybe this is also kind of confusing because it's kind of abstract, right? Then how about this? You just try keep going. Try keep going. 20 is 2 times 5, right? So you can write root 2, root 5. My bad. 20 is 4 times 5, so root 4 times root 5, right? You just keep going until you cannot go further. All right? So the strategy here is you just keep going, make the tree bigger until you cannot do even more. You cannot go further. And this is just a 3, right? And the root 4 is 2. So 2 root 5, 3. So 6 root 5. Better, Ether?
Yes, yes.
Yeah,
Thank you.
maybe, yeah, the criteria here maybe help some of you, but maybe confuse some of you. As I said, how about just keep just trying to go further as far as you can until you cannot go even further. Then you are through on that. All right, so that's topic 2. Topic 3, we're going to talk about the operations of complex numbers. Let's see, how do we add, subtract, multiply, divide complex numbers. The challenging part is the division. So for the addition, subtraction, multiply, I'm gonna do as fast as I can, okay? 6 and 7, let me get a problem. We do have an issue is our lumen does not provide as much problem as it should. Okay, the first question. Yeah, this question 6, number 6 in Lumen. This one. Perform the indicated operations and simplify. Very important. If you don't simplify, the system will mark it as incorrect. Give your answer in standard form. And all those words, it matters, okay? You should take time to read all those information. Let's add. So when you add, just trying to be no-brainer. Just do not think about I is imaginary unit or whatever. Just treat I as a letter. Just treat I as a letter, and you apply combining like terms. So we have 2 parentheses here. We're gonna remove the 2 parentheses because both of them has 1 as a coefficient. So when the coefficient of the parentheses is just 1, we could really literally remove the parentheses. So we have 22 minus 3i plus 10 plus 2i. Just don't overthink, huh? Okay, do not overthink. Combine like terms. Those are 2 like terms, and those 2 are like terms. Just combine them. 22 plus 10, 32. 22 plus 10, 32. Negative 3i, positive 2i, negative 3 plus 2, negative 1. So negative 1i, which is negative I. So the correct answer is already simplified. And in the standard form, 32 minus I. Very easy, right? I believe you can do that. It's pretty straightforward. Next is subtraction. You guys know distributive property, right? Distributive property applies when we need to remove grouping symbols. This one, we have square root of negative 25 minus square of negative 9. See those square of negative number? Use the formula right away and rewrite them in terms of I. Root 25i. Copy the subtraction sign in the middle. Root negative 9 is root 9i. Root 25 is 5, 5i. Root 9 is 3, 3i. They are like terms. You do not overthink. I believe you know how to combine 5x minus 3x, right? Very basic from foundation. They have exactly the same variable part, so they are like terms. They do not have the same coefficient, but it's okay. When we combine like terms, we're combining their coefficient. 5 minus 3 is 2, and bring down the variable part, so 2x. Right? So you can also understand this way. How about 5i 5i is just the I plus I plus I plus I plus I. Literally 1, 2, 3, 4, 5. 5 i's. That is what does 5 i's mean. And 3i literally means 3 i's. You know, I was thinking we have iPhone, iPad. I don't know if that have anything to do with the imaginary unit or it's just a coincidence. If it's a coincidence, I think it's a very cool coincidence. And the 5i minus 3i, basically you just need to remove 3 i's from the 5. Then you have 2 i's left. And done. And in the standard form, let me try. Let me try if I enter. I don't have to show you. I'm in Lumen right now. I'll let you know. If I only enter 2i, would the system identify as correct without the right 0 plus 2i? If I only enter 2i, let me see. Yes, still correct. All right. Yeah, technically it is 0 plus 2i, but if you only enter 2i, the system will identify it as correct. All right. So that is this problem. So we covered addition, subtraction. I hope this helps. Pretty straightforward. There's really nothing to elaborate on this. Multiply. We're going to practice 5 problems. The first problem, number 9. Do you guys like a FOIL or do you guys like a box method? For the first problem, I'm going to use both. And then you tell me which method you like, all right? Okay, this problem. Add a page breaker here. Okay. This is a multiplication of 2 complex numbers. Each complex number has 2 terms. The 2 parts, you know, -3 is the first term, -i is the second term. I'm using the terminology term. What is a term in foundation? A term is an expression without addition, subtraction, or anything else. A term is an expression only contains multiplication or division. Well, I don't want to confuse you with those definitions. You see 2 things in the first parenthesis, 2 things in the second parenthesis. So we can use either FOIL or box method. Let me show you FOIL first. We have -3 minus I times 2 minus I. I'm gonna color them differently, okay? Blue, green, yellow, pink. The method is called FOIL, F-O-I-L. F means first, O means outside, I means inside, L means last. First, okay, do you see that the blue and the yellow? The blue, 93. I'm also saying the number. The 93 in the first parenthesis, the blue, is the first term in the first parenthesis. The yellow 2 is the first term in the second parenthesis. So when we say first, we are referring to those 2. The blue and the yellow, they are first. Outside, as you can see, you have 4 things, right? 4 terms, 1, 2, 3, 4. The blue and the purple, they're on the outside. Blue 93 and the purple -I, they're on the outside, right? And they are outside. Inside, the green and the yellow, -I and the 2, they're on the inside. Last, the green -I is the last term in the first parenthesis. The purple -I is the last term in the second parenthesis. So they are last. So for FOIL, you should firstly set up the structure, like what I'm trying to do here. parentheses times parentheses plus parentheses times parentheses plus. Yeah, what is the structure? Set up the structure for FOIL. FOIL, F-F-O-O-I-I-L-L. F-O-I-L. You have 4 terms added together. Notice we have addition sign in the middle, and each step has 2 parentheses multiplied together. Parentheses multiplied with another parenthesis plus parentheses minus multiplied by another parenthesis. So see the structure here. Now I'm gonna fill in the 8 blanks. First, do you see the first, the blue and the purple, blue and the yellow? First. 93 is the first term in the first parenthesis. 2, the yellow 2 is the first term in the second parenthesis. So that is the first. Just put them here. Yeah, one for each slot. Outside, blue and purple, outside. Blue, -3, purple, -I, outside. Inside, green and yellow, -I, 2. Inside. Last, green, purple, -I. You see that? Do one thing at a time. You want to enjoy a meal, do one bite at a time. If you want to do a lot of things in one, you very high chance messed up, and you have to. It's just a waste of energy. So next step. This step, all we do is to set up the structure and fill in the 8 blanks, right? Next step, we do the simplification. -3 times 2, -6. -3 times -I. Knowing this is not -3 minus I, because we have a parentheses. Why the parentheses here is so important? Without the parentheses, you confuse yourself. There's a chance you confuse yourself. You think that's -3 minus I, right? No, it's -3 times -I. Negative times negative is positive. Positive 3I. Next, -I times 2. And we can switch the order. The commutative property still applies. So -2I. Last, let's spend time. Do not do it in your head as a beginner. Do not do that in your head. What is this? -I times -I. It's not -I minus -I. Okay, this means multiply. Firstly, negative times negative is positive. So no sign. And then I times I is I squared. What is I squared? I squared is -1. Okay, very important. Because I is root -1. So I squared is -1. Okay, yeah, this is a very important feature. You know, actually, I should add this at the very beginning with the imaginary unit formula. Compare with this formula, root -1 is I. A more important formula is I squared. I'm gonna read out this one. Is I squared equals -1. Insert this one. I squared equals -1. More important formula is this formula. All right? Yeah, that's very important. Very important. Okay, let's go back. What is I squared, guys? What is I squared?
-1.
Perfect. Yeah, I squared is -1. Where were we? Okay, so I squared equals -1. So last times last is -1, right? And then keep simplifying, combine like terms. -6, -1, -7. +3, -2, +1. 1I is just you don't really write 1 out. So the answer is -7 plus I. That's the first method. Second method, box method. If you want to use a FOIL, use the procedure I just applied. Try not to skip steps. When you want to skip steps, really easy, just messed up. So box method is you make a box, 2 rows, 2 columns, and then you write one complex number on the side, -3, -I. The other complex number on the top, 2, -I, and then you multiply, then fill in the 4 cells in the box. 3 times 2, so this here is the multiplication of 3 and 2. Okay, because this spot is the intersection of 3 and 2. So we're going to multiply 3 by 2, 6. And this spot is 3 -I, right? So you're going to figure out what is 3 times -I. Negative times is positive, so positive 3i. And this spot is row 2, column 1, right? So we should multiply 2 and -I together. Double -I, we have -2i. And this spot is -I times -I. I do that already, right? We can do that again. -I times -I. So, okay. So firstly, -I times -I, they are both negative. Negative times net is positive. So we have I squared. And I squared equals 1. And in the middle, those two can also combine. And the other two can be combined. So we have 7 plus I, and done. Yeah, whatever method you use, give it a try. Give both methods a try to see which method is for you. Everybody's different, right? That's number 9. Number 16. Yeah, I'm gonna give you a chance to practice. Hold on. Yeah, number 16. This one. Oh, okay. This one is different. Number 16 and 17 and 20. 17 and 20. Okay, finally. I want you to practice this one. That one is very easy. Don't need this much space. This one might take a little bit. So we just introduced 2 methods to multiply complex numbers, right? Try this one. Try this one. I give you a couple minutes. Oh, it's already 43. We have to finish today. How about you do that later? And how do we process this one though? If we multiply a number, real number, by a complex number, just use the distributive property, okay? 5 times 2 plus 5 times 9i. 5 times 2 is 10. 5 times 9 is 45i, and done, right? And what if you have something like this? Non-real imaginary times a complex. Same thing. Do distributive property, all right? 2i times 5 plus 2i times negative 9i. Be careful with the sign. 2 times 5, 10, 10i. And here 2 times negative 9 is negative 18. And I times I is I squared, right? And we have 10i here, negative 18i squared is negative 1. 10i. Negative 18 times negative 1 is a positive 18. So the standard form is 18 plus 10i. A common mistake to avoid when we apply this formula. For example, square root of square root of 2 times square root of 8 is square root of 16, right? And square root of 16 is 4. So this formula is only true when both a and b are non-negative. This is only true when both a, b are non-negative. If we have, let's say, root -2 times root -8, you cannot apply this formula and include you have, okay, we have root, this is wrong by the way, okay, root 2 times root a, -2 times -a is the square root of 16, which is 4. This is incorrect. You can't do that. Remember earlier I mentioned whenever you see square root of negative number, you need to right away rewrite the square root of negative number in terms of I. So this is root 2i. This is root ai. Root 2 times root a times I squared. Root 2 times root a, you can use this formula. That is root 16. Root 16 is 4, and it's 4i. It's not, sorry. Not, it's I squared. I squared is negative 1, so negative 4. It's not positive 4, right? It's negative 4. You can rewatch this part later. You don't really have this in the homework, but this is important. And this involves multiplication. So I don't want you to make any mistake. Just in case you see something like this, you do not rush to use that formula because that formula is only true when the radicands are non-negative. If it's negative, you should, again, when you see a square root of negative number, right away, first thing to do is to rewrite the square root of negative number in terms of I. Division. 5 minutes for division, a little bit challenging. I'm gonna prove this formula first, all right? A plus bi times a minus bi. I'm gonna use the box method. This is abi, this is a negative bi. A times a squared. A times negative bi, negative abi. A times bi, abi. Bi times negative bi. Bi times negative bi. This is not minus, okay? Not 0. It is positive times negative is negative. So negative b squared, I squared. We know I squared is negative 1. Negative 1 times negative 1 is positive 1, so we have b squared here. And those two terms, look at them. They are opposites. They cancel each other. So we have the result equals a squared plus b squared. When we have two complex numbers, they have the same real part, but opposite imaginary part. The imaginary part of the first complex number is b, right? The imaginary part of the second complex number is negative b, or opposite. Then we call they are conjugate of each other, okay? A plus bi and a minus bi are conjugate. And you need to know that. It's not difficult to know. This basic. When you multiply the two complex numbers together, the result has no I. the result a squared plus b squared is a real number. Okay, is a real number. And that's the reason we need to use conjugate when we divide complex numbers. An expression, if we have I in the denominator, we consider that as not simplified. So we have to get rid of I from the denominator. To do that, we use a conjugate. For example, we have 3 minutes, 20, let's do 14. If we don't finish, then we just continue next time. Division actually is a difficult and important topic. Okay, I'm gonna get this problem done in 3 minutes. Bear with me. 6 plus I, 4 minus 3I. Firstly, identify the conjugate of the denominator. The denominator is 4 minus 3I. The conjugate is 4 plus 3I. That's the conjugate of the denominator. And then multiply both top and the bottom by the conjugate. 4 plus 3I. 4 plus 3I. Denominator, 4 minus 3I, 4 plus 3I. Either FOIL or box method, or you can just use the formula. The more tools you have, the more efficient you can solve a problem. If you don't know this formula, you would have to FOIL or box method. But if you know this formula, you can just quickly apply it. I'm gonna quickly apply it, okay? Because the denominator, 4 plus 3I and 4 minus 3I, they are conjugate. When the two complex numbers are conjugate, the result, the multiplication, is the real part square plus imaginary part square. 4 square plus 3 square. 4 square is 16. 3 square is 9. 16 plus 9, 25. So that's the denominator. Numerator is 6 plus I times 4 plus 3I. We don't have a formula to use. So let me use the box method quick. 6 plus I, 4 plus 3I, 4 times 6, 24. 3 times 6, 18I, 4I, 3I squared, 93, because I squared is 91, right? Yeah. 3I times I, 3I squared. I squared is 91, negative 3. Those two combine, 24 minus 3, 24 minus 3, 21. 18I plus 4I, 22I, almost there, bear with me. And now we're gonna flip. The top has 2 terms, bottom has 1 term. We're gonna use the top one, the first term in the top over the bottom, plus the second term on the top over the bottom. And that gives us 21 over 25 plus 22 over 25, and then I. Any questions? I was a little bit too fast. We will continue on Tuesday. We'll practice more about division of complex numbers. All right. Knowing adding 2 complex numbers, the result still complex number. Subtracting 2 complex numbers, result still a complex number. Multiply 2 complex numbers, the result still a complex number. Even when we divide a complex number by another complex number, the result is still complex number. As you can see, we have the result in the standard form, a plus b times I, right? Okay, we're gonna stop here. I'll see you on Tuesday, guys.
See you Tuesday. Thank you.
You're welcome. Bye.
Bye, thank you.
You're welcome. Bye-bye.